Okay, folks, this is a video on a subject called connected objects or systems. So unfortunately, I use both of those names interchangeably. You will know it's this kind of problem because there are multiple objects connected to each other, and we're going to find the acceleration of the system and then find the tension in the ropes. Okay, so you'll get this type of problems. All right, so we're going to start with a little story. So Jade is giving Lucas a ride home from school, and oops, they get stuck in the mud. Who do you think should push the car out of the mud? Okay, so Jade asked Lucas to push the car out of the mud, and Lucas is lazy, clever, and attractive, and he was like, I have my nice Italian shoes on, and I do not want to get them muddy. So, oops, he says he will stay inside the car and push on the dashboard instead of getting outside and pushing on the bumper. He's sitting nice and dry in the passenger seat and pushing on the dashboard in front of him. Will his plan work? Okay, hopefully this makes sense to you, even if you got it wrong. By Newton's third law, if Lucas pushes on the dashboard with 80 newtons, the dashboard pushes back on Lucas with 80 newtons. So the net force on the system is 0. So if we zoomed in inside the car, and this is Lucas, and he pushes on the dashboard with 80 newtons, then the dashboard pushes back with 80 newtons, and those two forces cancel. Okay, so that's why I have the corollary that you can't propel yourself, you have to push on the environment. So if he gets out of the van and pushes on the van with 80 newtons, then the van pushes back on him with 80 newtons, and we hope he has enough static friction to keep him in place, but he's now the environment pushing on the van. Okay, so you don't need to write this down. I just want you to think about what I mean when I say it's a system. It's a set of objects is a system when every object in the system has the same acceleration. And they're going to be forced to accelerate at the same rate because they're connected by ropes or internal normal forces, which are a little tricky, but you will get practice with that and we'll see some real-world demos. Okay, so again, you don't need to write this statement down. I just want you to kind of know what we're looking at. And then you will draw one force diagram for, let's say there's 3 objects like the very first slide. You'll draw one force diagram that includes all of the forces on all 3 objects. And then we will isolate individual objects to focus on them just like we did in the previous unit. All right, this you need to write down. Internal forces are interactions between 2 objects in the system. So when Lucas was inside the van, the force between him and the dashboard was an internal force. And by Newton's third law, these forces will always cancel because they're always going to be equal and opposite. And so therefore, internal forces cannot affect the acceleration of the system. Please write that down. External forces are interactions between an object that is in the system and one that is outside of the system. So when Lucas got out of the van and pushed on the van, he then became an external force. So there is one force that, for the most part, for us in this class, one of the forces you already know, we must never forget this, is always an external force. Okay, hope you guessed right. Weight is always an excuse me, an external force, because when the bowling ball is falling, it's the attraction between the bowling ball and the earth is never going to be part of our system. So weight is always going to be an external force. We're going to take one more slide, and then I'll do the problem example in a different play posit. So I put new in quotes because this is really Newton's second law, the sum of the forces equals ma, rewritten. So the acceleration of all three objects in the system on the first slide of the slide deck is equal to the sum of all the forces that are parallel to the motion, and we'll go over this when we do the example problem. So two things have to be true about a force to put it in the numerator. It needs to be either with or against the motion, so parallel or anti-parallel, and it needs to be external. It needs to be caused by an object outside of what we're defining as our system. So this is me trying to learn LaTeX and being kind of awkward, but it's the sum of all the forces that are parallel to the motion or anti-parallel and external. And the denominator is super, super easy. Every single object in the system brings inertia to the party. So the denominator here would be 12 plus 3 plus 5, or 20 kilograms. The denominator is super, super easy. Find everything that's moving. Everything that is moving has inertia, and your denominator is just going to be the sum of all the masses. Super easy. All right, that's the big picture conceptually, and then in the second play posit, we'll do an example problem. Thank you for listening.